So this is what we've been looking at in from the theory point of view. There is a flow turning angle theta and the shock wave angle beta and the inlet microwave. So this is the m beta theta relationship which we have derived, and in the limit of theta tend to 0, there are two possible solutions. Either it could be a normal shock wave, or it could be a Mach wave, or a normal shock wave. So this is the graph what we have discussed here. So here on the top you have this strong solution, this is the weak solution. And one of the things which I should have mentioned here is that when we have an oblique shock, flow encounters oblique shock, the flow will decelerate, but it will not become subsonic. But when you have a normal shock, the flow will become subsonic. But when a flow encounters a shock, is a process of deceleration. Whether it's a normal shock or an oblique shock, the flow will decelerate. Okay, but in the case of normal shock, it will become subsonic, strong deceleration. But in the case of oblique shock, the flow will decelerate, but it will still be subsonic here. Now this is the table. If you take your tables here, this is the graph what you see here. Now without this theory, it would have been much difficult for you to understand, but now with the theory what we have dealt, now you know how this, the details of the graph what you see here. Okay, so this is basically m beta theta relationship. If you want to make some small notes there, on the x-axis you see the deflection angle. Deflection angle is the same as the flow turning angle. In the NACA table they use delta, we use theta. So if you want, you can strike it and put it theta there. Theta. So this is the angle, flow turning angle, theta. So deflection angle is the same as the flow turning angle. And on the y-axis, shock wave angle is given as theta. We used beta. So you make a note of that also. So once we come back from the T, we will go back to the problems, and we'll try and work out a couple of problems to understand how this shock flow interacts with the oblique shock. Let's try and work out the problem. Problem number 4, oblique shock. An aircraft flies at a supersonic speed of Mach 3. The corresponding free stream static pressure and static temperature. So problem number 4 of oblique shock. The static pressure is given as P1 is given as 1.0133 bar, and the static temperature is given as 300 K. Air in contact with the frictionless inlet is deflected at an angle. So deflected means you have this information, flow turning angle, deflection angle is given as 15 degree. Assume that this results in a weak shock wave. Okay, calculate the static pressure, density, temperature, velocity, all downstream of the shock. So P2, ρ2, T2, and V2 and M2 downstream of the shock. Calculate also the change in stagnation pressure across the shock. What is delta P T? So what is PT1 minus PT2 across the shock? So these are the parameters. So the key point what you see here is that the flow is now deflected and has a weak shock. So this is a typical problem of an oblique shock. So here is the flow encountering the oblique shock. This is the shock wave angle beta V1. We have no information of V1, but we have information M1 is given as 3, and we have the information, so this is 1 and 2. So here is the normal component of it. So P1 is known, T1 is known. The flow after passing through the oblique shock will turn by an angle theta, which is equal to 15 degrees. So we are asked to find out what is P2, T2 rho 2, V2, M2, PT1, PT2. So how do we proceed with this problem? We don't know the angle beta, but we know from the theory what we have learned from the M beta theta relation. We can say that if M is known and if theta is known, M is 3, theta equal to 15, we can find beta. So to do that, go to this graph, find the value for M equal to 3, and find the value of theta equal to 15 somewhere here, and then project it to find beta. So what is the angle you get for beta? 32 degrees. Now we know that. All of you got this one? Yeah. Shall we move on? All of you got the value for beta as 32. So once you have the value for beta, so we know that we are dealing with a problem which is not a normal shock, it is oblique shock. So if we wanted to calculate anything, we need to make sure we resolve it so that we have the normal component V1n or M1n. And then we can then treat this as a normal shock problem using the normal shock tables here. So this is M2n. So M1n is equal to M1 sine beta. That's what we have here. So here it is M1 makes an angle beta with the oblique shock. Resolve it, you get M1n. So M1 is given in this problem as 3, and you have already found out beta to be 32. What is M1n? How much? 1.59. Now, for that value as 1.59, you can look at the table to find M2 from the normal shock table. Yeah. Go to the normal shock tables. Are you able to understand this? And then find M2. That will not be M2. That will be M2n for us. How much you said? 0.675. Okay, let's first gather the data and then we will then proceed with analysis. So for that value of M1, we should be able to find P2 by P1, T2 by T1, PT2 by PT1, and so on. Yeah. Also, we can find rho 2 by rho 1. What is P2 by P1? 2.783. And what is T2 by T1? 1.3381. Yeah. What is PT2 by PT1? 0.8989. And rho 2 by rho 1? 2.015. Now, P1 is known to us. From this, we can find P2. Similarly, we can find T1.
M2 is 6.6715. 1.67.
0.6715. Okay. Thank you. So what is the value for P2? 2.82 bar. T1, sorry, T2, 414.3 Kelvin, and can you find PT2 by PT1? You can use this expression PT1 by P1 is equal to 1 plus gamma minus 1 by 2 M1 square power gamma by gamma minus 1. That will give us the value for PT1. What's the value for PT1? $37.2 37.09 kilopascal. Okay, bar. So what will be the value for PT2? $33.84. 34. PT1. Did you use the value for 3 here, Mach number 3? That
P1 by PT1 relation for 1.59 mass.
Yeah, but that is for, but listen, here we are looking at a problem. Let me look at it here. So here is the oblique shock. Here is the state before oblique shock. Here's the state after oblique shock. Now the flow is encountering this oblique shock with a velocity v1 or m1. Now this will have two components. One is the horizontal component and the normal component. And here it is m1n. And here it is m2n. We resolve it to get the property variation across. But here, if you look at even before, here we have P1, here we have T1, and here we have M1. So the properties before itself is it is PT1 by P1 is equal to 1 plus gamma minus 1 by 2 M1 square. It is not M1n. M1n is helpful to find how the property changes across the shock. That's what we discussed it from the theory. Okay. This is the flow before encountering the shock. So that is the Mach number is M1. M1n, we are deducing it, we're deriving it to get how the property changes across the shock. So what is the value? This one? 30?
Instead of using this relation at Mach number 3, we can use this PT by PT1.
You can check that value, what value you get. 30?
That is 7.2.
2 bar. That's 7.2. You can cross check that and so this is the total pressure here, but then you can use this M1n relationship to find what is the pressure PT2. What is PT2? 30? 4.5. Rho 2 by rho 1? You need to find rho 1 because there is no information of rho 1. P1 is there. Rho 1 is equal to P1 by R T1. Find the value for rho 1. What's the rho 1? 1 point something? 1.17. And then rho 2? 2.37 kg per meter cube. So what have we calculated all the parameters? We are asked to find out P2. We have calculated PT2, static pressure. We have calculated the static temperature. We have calculated the static density. We have calculated the stagnation pressure. We can then find what is PT1 minus PT2. That is the pressure change. 37.22 minus 33 point something, whatever we got. What's the value? 3.77 bar is the pressure drop across. Total pressure decreases by that value. Now, we still have two more parameters to calculate. Now we can see from here in this picture, the flow that comes in at M1 will turn by an angle theta, and that will be M2 or V2. The flow itself makes an angle beta minus theta, and what we have learnt is M2n is equal to M2 sine beta minus theta. Now you have already found out what is M2n from the table, which is 0.6715. So this is known. Beta you have found out as 32, theta given in the problem. So you can find M2 as M2n by sine beta minus theta. Yeah. how much? 2.2 2.28 or 9? 2.23 or 2.3? Okay, 2.3. That's the Mach number. So now you can see that the flow has decelerated from m1 equal to 3 to 2.3. The flow has decelerated. It didn't go to subsonic. It is still supersonic. That's how it should be. So V2 is equal to M2 C2. What's the value?
It's 938.4.
Meter per second. So now you have learned how to, we have understood an oblique shock theory, and then we have also applied it, and we'll try further to understand a bit more of this oblique shock problems. Yeah, so now you know how to handle the oblique shock. Okay, so I would like to solve one more problem. That's problem number 5 before we go for lunch. But before we go for solving this problem number 5, we need a bit more of information, which is something I'm just going to look at it. I will be covering shock interactions and reflections. This is more like a corollary. So if this is what is happening, this is what will be the effect. Yeah. So which I'll be doing it tomorrow morning before I start with the flow structures in supersonic nozzles. But just quickly to cover some of the stuff what we are going to do in problem number 5. So for example, if you have a wedge, so you have a wedge. So you have a wedge here. This is what you see here, a wedge here. When the flow encounters a wedge, the half wedge is the half wedge will be the turning angle theta. So the flow that comes in here will encounter this oblique shock and will turn exactly by the angle theta. So now you can see the benefits of it. The oblique shock will cause the flow to go parallel to the surface. If there had not been an oblique shock, the flow will come and hit the wedge, because the wedge is going like this, and if there not be oblique shock, the flow will come and hit the wedge. Now because of the oblique shock, the flow will turn and will go parallel to the wedge under supersonic applications, and this flow will turn exactly by the same angle the wedge has turned. Okay, so that is what we see here. Now you can see that when you have full wedge, there will be shock of this is of one family, this is of the opposite family. So but the principle is the same. So when a flow encounters a shock concave surface, there will be an oblique shock. So this is the oblique shock of one family, and this is the oblique shock of the opposite family. But when you are having a flight at this situation, then you have an equal angle of attack. But under takeoff mode, it will be different, a different angle of attack here. So when if it is unsymmetrical, now you will not have theta 1 is different and theta 1 prime is different. They are not same. Accordingly, the flow will turn differently. That's what we need to know. Okay. Now what will happen when you have an oblique shock coming from here? Okay, a wedge has deflected there's an oblique shock. But this is the so what will happen when you have an oblique shock that is coming is going to hit the wall. So that is what you're going to look at here. Shock reflections, solid wall, like reflections. So here is a situation when you have a wedge, you have an oblique shock, the oblique shock hitting one, you have a like reflection of opposite family. This is a reflected oblique shock, what you see here. So here you see a reflected oblique shock coming up here. The function of the reflected oblique shock is, so now let's look at this here. If there's a flow coming in here, this is at an angle theta, the flow turns by an angle theta. If there is no intervention, the flow will go and hit the wall. Is that clear? If there's no intervention, flow will hit the wall. Before the flow hits the wall, the oblique shock that has hit the solid wall will have a like reflection. Like means an oblique shock hitting, there are two things. One is an expansion wave, which will be coming later on, Prandtl-Meyer expansion waves. So when we have an oblique shock hitting the solid wall, it also results in another oblique shock. That's what we call the like reflection, but then it looks of the opposite kind. Before the flow hits the there will be a reflected shock that will make sure that the flow doesn't hit the wall. Instead, it will cause the flow to turn exactly by the same angle which is has turned before, so that now the flow goes parallel to the wall. Is it clear? If there is no intervention here, then that flow will turn and hit the wall. But now before the flow hits the wall, the reflected shock will come in and will cause the flow to turn exactly by the same angle it has turned, and it goes parallel to the. So that is what will happen here. Now, if you look at it, so here is M1, the flow will decelerate. So M2 will be less than M1, and then again the flow will turn exactly by the same angle which it has turned. So here you can see that this has turned by an angle theta 1. This is theta 1. Again, the flow turns by an angle theta 1. The flow decelerates. Now we see M3 will be less than M2. So that's what we see. We see the deceleration process. The overall strength of the shock is assessed by the pressure ratio, static pressure ratio. What's the overall strength of this one? This is P3 by P1. So here it is 1, 2, and 3. So here between 1 and 2, from here moving from 1 to 2, moving from here from 1 to 2, the pressure P2 will increase for the reasons what we discussed this morning here. Flow encountering oblique shock, there's energy transfer, there's the pressure increases, temperature increases. Again, the flow going from 2 to 3, the pressure increases. Same with the temperature. But the total energy remains constant. Yeah. So HT1 is equal to HT3 across the shocks. Okay. With this understanding, let's now solve problem number 5. Air, assumed to be a perfect gas, flows between two parallel frictionless walls. So two parallel frictionless walls. The initial flow Mach number, so it's a, I don't know whether this one will cover M1 equal to 4. Oh, so it is not here. The data is not there, I think. Yeah, we have, no, it's only up to 3.9 is there. So shall we'll change it to, for current, let's say it's 3.5. I didn't print those table there, that part of it. So let's say it is M1 is 3.5. The initial flow Mach number is M1 is 3.5. Let's say that the lower wall abruptly turns the flow into a turning angle of 20 degrees. Now you can see that I don't know whether the parameters are matched, but anyhow, we'll try. Let's understand the principle of it. The flow, which means the flow is abruptly turned by an angle of 20 degrees. The lower wall abruptly turns. Determine the wave angle of the initial oblique shock. When you have a supersonic flow encountering a concave surface, immediately there will be an oblique shock. So here you have an oblique shock that is being formed. Here you have an oblique shock that is. Now oblique shock is going to hit the upper surface of the solid wall. Because it is going to hit the solid wall, there will be reflection. But before that, let's see what happens here. The flow that comes in here, the flow will turn exactly by the same angle of 20 degrees. So here it is M1, here it is M2. This is the pathway it is going to take. But before it hits the wall, there will be a like reflection of opposite family . So this is the shock wave beta 1, M2. Now this will have an angle beta 2. Is that clear for all of you? Now the flow will not hit the wall. It will go parallel to the wall, which means the flow will turn exactly by the same angle, 20 degrees, and then go in this direction with M3. Is that clear? So this is what the problem reads. Assume air to be a perfect gas, flows between two parallel frictionless walls. The initial flow Mach number M1 is 3.5. The lower wall abruptly turns into the flow. It's a concave surface and it turns by an angle of 20 degrees. Determine the wave angle of the initial oblique shock wave. What is beta 1 from the lower wall, and the Mach number M2, what is M2 after the shock wave 1. If the first oblique shock, this is the oblique shock 1, here is the oblique shock 2, which is the reflected oblique shock. Oblique shock 2 is the reflected one. It reflects the upper surface. Determine the angle of reflection of the oblique shock. So what means find what is beta 2 and what is M3 after the reflected oblique shock wave. You have? Okay, so you can, let's go with that one. Yeah. Okay. But you can use the chart. Yes. Sorry. That's true. Yeah, you can. Yeah, we are going to use only that one. So when we have more number of shock waves, best way to avoid confusion is to put a subheading as oblique shock wave 1, because you will see that you will have and M1N here for oblique shock 1, and here you have M2N. This is the M2N is the outgoing from the first oblique shock. Now again you can see that then there will be more complications here. So this will be M2N entering the reflected one. To avoid all this confusion, let's go by shock wave by shock wave. Oblique shock wave 1, M1 is given as 4. Flow turning angle theta is given as 20. What is the corresponding oblique shock wave angle? Beta 1. That's what we're asked to find out. What's the value for beta 1? 32. You don't need to interpret, but be as close as possible. So, yeah. 32 or 32 point something, 5 or... Yeah. So for the sake of consistency, shall we go with 32.5? So 32.5 degrees here, because it is in between these values. So the way forward is to look at this M beta theta for 20 degrees. Find what is this one here, 32.5. So we have found out the value for beta. Now you can see it's much more simpler. Now how will you find M2? Now use this value, find M1N. M1N is equal to M1 sine beta 1. Find M1N. Two. M1N 2.15. For this value of M1N, you can find what is PT. You can find what is P2. You can find almost all the properties. PT2 by PT1. You can find P2 by P1. You can find T2 by T1, and so on. But in the problem, we are not asked to find those parameters, but you can find. You can find, but it is not asked. And you know how to find these values there, because we already done in the previous problem. But in the problem, we are asked to find out what's the value for M2. What's the value for M2? How will you find M2?
Chart will take 2n. The table will take 2n.
Yeah, find the value for M2N from the table. What's the value you have? 0.554. And then now we have to look at the shock that is coming out of this one. So we have M2N is equal to M2 sine beta 1 minus theta 1. So from this you can find m2 is equal to m2n by sine beta 1 minus theta 1 2 How did you find from the chart? For the last chart one, yeah? Yeah. So it's not very far from this one. So of course there will be the truncation part of it. So it is m2 is 2.56 and find out beta 2. Now if we come across a situation where the flow, here is the oblique shock. The flow is at an angle beta. So this is the, you can look at it like this. So here is an oblique shock where this is m2 and this is at an angle beta 2. The flow encountering the oblique shock will turn by an angle theta. This is again, what is this angle theta? Same angle through which it has already turned. What's that angle? 20 degrees. So again, m2 which you already calculated, theta 2 which is the same as 20 degrees, 2.56. What is the value for beta 2? Forty 41.5 degrees. So finally we are asked to find out m3. So then we find, now again before we proceed to this, put this oblique shock 2, that's the title there, because for again we are looking at m2n will be m2 sine beta 2, because you find m2n coming for each and every shock. Find m3n, find m3n, What is M2N? 1.69. M3N? What is it? 0.64. M3N is equal to M3 sine beta 2 minus theta 2. So from this, M3 is equal to M3N by sine beta 2 minus theta 2. What is the value for M3? 1.774. So now you can see that we are able to decelerate the flow all the way from 4 to 1.4 by using train of shocks. Yes, so with two shocks. If we want, we can find what is the strength of the overall strength of the shock wave. So which is 1, 2, 3, which is P3 by P1, which is equal to P3 by P2 into P2 by P1, which means you have to find the values of the pressures across the value of M1N and M2N. Okay, but that is how you can calculate it. All of you have solved this problem now? Yeah. Shall we attempt problem number 6? Problem number 6. Compare the loss in total pressure ratio incurred by a two-dimensional 2-shock spike diffuser and the 3-shock diffuser operating at Mach 2 as shown in the following figure. Assume that each oblique shock turns the flow through an angle of 10 degrees. Each oblique shock turns the flow through an angle of 10 degrees. So there are two problems here. First is 2-shock configuration. Other one is the 3-shock configuration. We haven't gone into the inlets. We will be going into the inlet bit later this afternoon. Now, so here is this an external compression inlet. So here, this is the geometry here. This is the inlet of the engine. We will be discussing this afternoon. So here is the spike leading edge. This holds an oblique shock. So it's problem number 6. Holds an oblique shock. Then here, this flow that encounters this oblique shock will turn by this angle theta so that it doesn't hit this one. So the flow turns, and before it enters into the inlet of this engine, it encounters a normal shock wave which is at the throat. The minimum area is here. So this is the normal shock, which is not explicitly given in this problem here. Yeah. So this is a normal shock. So here is the first part is 1 oblique shock, 1 normal shock. The second one is 2 oblique shock and 1 normal shock. So one thing is very clear. Once the flow encounters the normal shock, it becomes, so here it is M1, M2, M3 will be subsonic. Now once it becomes subsonic, now what you can see here is that you can see it enters into a diverging geometry. The pressure will still increase before it enters into the combustor. Is that clear? So we are decelerating the flow from Mach number 2. In the process, we are increasing the static pressure from P1 to P2, and then we increase it from P3. Then again, we still continue to increase it. In this particular problem, what is to be calculated? We are asked to calculate the total pressure ratio or pressure loss. This is what they're asking here. So here it is PT1, here it is PT2, here it is PT3. We don't know any information. Here it will be PT4. we are asked to find out what is the inlet pressure recovery. Otherwise, what is inlet pressure recovery, or what is the, or yesterday we looked at it as pi d. Pi d, what did we look at as PT2 by PT naught in the subsonic inlets problems. So we are asked to find out what is the pressure loss, which is PT3 by PT1. PT3 by PT1 is equal to PT3 by PT2 across the normal shock and PT2 by PT1 across the oblique shock. 1. So this is the first part of the problem. The second part of the problem is you have dual compression ramp. So this is the first compression ramp. Then there is another concave edge. So something like this. So there is a leading edge here, the spike, which holds this oblique shock 1, which causes the flow coming in at M1, will cause the flow to turn exactly by the angle theta 1. So it turns. But then this flow will go and hit this convergent part of it. So the second oblique shock is initiated from the concave surface of the second part of the compression ramp. So this is oblique shock 2. So here the flow encounters. Then the flow turns further by the angle through which it has turned theta 2, and it enters into the engine. Then this is the normal shock. This is the normal shock. Sometimes this normal shock is also called the terminal shock. And we will study all these things in the afternoon. Yeah, terminal shock. So here it is M1, M2, M3, and then it goes to M4. M4 will be subsonic. So here it is 1, 2, 3, 4. We're asked to find out what is PT4 by PT1, which is PT4 by PT3 corresponding to the normal shock, and PT3 by PT2 that corresponds to oblique shock 2, and then PT2 by PT1 that corresponds to oblique shock 1. We are asked to find out what is PT4 by PT1. We are asked to find out what is PT3 by PT1 and compare which inlet has better inlet pressure recovery. Understood? So to solve this problem, you first draw this one part, problem number 6. Have this as part A, and then have this as a, give the label oblique shock 1, and then give the title normal shock. Then find out what is PT3 by PT1. Find the value there. Then go to part B of the problem. Give the title oblique shock 1. Find out what is the pressure ratio PT2 by PT1. Then go for oblique shock 2. Find PT3 by PT2. Then go for normal shock. Find PT4 by PT3. Then find out what is PT4 by PT1 and compare these values. Is it clear what you should do now? Yeah? Okay, you can start the problem, solving the problem now. Now you work out the problem and then tell me what is the value for PT3 by PT1 for part A. Come on, you can start solving it now. To make it simpler and easier, it is just given only 10 degrees, same value. So problem number 6. Here is the oblique shock 1. So here is a M1, which is 2, and the floor turns by an angle of 10 degrees, and which is M2, and here it is M3. So for M1 is equal to 2, so this, let's put this as oblique shock 1. M1 is equal to 2, theta is equal to 10. Find beta. What's the value for beta? Beta is 39 degrees. What is M1N? (1.26). For that value, you can directly find PT2 by PT1. Should be 0.98. Nine eight 9857. Since you have found M1N as 1.26, directly you can find what is M2N. 0.071. From this you can find M2. How much? 1.665. Now this M2 is not going to have any oblique shock. It is going to go through a normal shock. It's just a normal shock. So directly you can read from M2 value there. That's a normal shock one. Zero point 0.87. Okay. Is that what everybody getting? 0.87. Then you can find out what is a total pressure recovery. PT3 by PT1 is PT3 by PT2 of normal shock, PT2 by PT1 of oblique shock. Just multiply these two values here. What is the value you get? Inlet pressure recovery 0.8866. 0.85. So which means that there is a loss of about 15% is the loss. We are able to recover up to 85% of the pressure. Okay, so with one oblique shock, with two shock trains, one oblique shock and normal shock, we are having a loss of 15%. Okay, now we'll try and work out the second part of the problem, part B. Here is the first compression ram, second compression ram. Here is the oblique shock 1, oblique shock 2, and then here is the normal shock. So this is the angle theta, which is the same in all the cases here. So it makes our life easier. So here it is M1, the flow turns by an angle theta to have the M2, and then the flow turns to go normal to it. So here it is M3, this is M4, 1, 2, 3, 4. So let's put the title oblique shock 1. What is M1N? So before that, M1 is 2 and theta is equal to 10. Then you have found the value beta as 39. So can we take it for granted that we have the value for PT2 by PT1 for oblique shock 1 as 0.9857, and because of this we have M2 value is, what's the value for M2 you got? 1.66. Now this is having an angle theta as 10. So what's the value for beta 2? That's something you need to do from here. How much? 48 degrees. So what is M2N? M2N. So this is the oblique shock 2. M2N is equal to M2 sine beta 2. What is the value for M2N? 1.23. Okay. For that value, what is the value for PT? What is it? PT3 by PT2 for oblique shock 2. .9896. Once you have got that value, from M to N, you can find what is M3N. What is M3N? How much?
0.8241.
0.8241. And this is equal to M3 sine beta 2 minus theta. From this you can find M3 is equal to M3N by sine beta 2 minus theta. So what is the Mach number after? How much? 1.76.
1.34.
1 point. This Mach number you're talking about. 1.34. Yeah, 1.34. So for a M3 equal to 1.34, what is the PT4 by PT3? This corresponds to normal shock. So this should be 0.9718. Now we have got most of the parameters. Now let's work out what is PT4 by PT1, which is PT4 by PT3 corresponding to the normal shock. PT3 by PT2 corresponding to oblique shock 2. PT2 by PT1 corresponding to oblique shock 1. What is it? 0. 0.9479. So you can see that you are able to recover much more of the, so the loss is in the order of 5%. So as a rule of thumb, it's always better to decelerate the flow over number of shock waves. That's what we learned from this simple example. So you find this more beneficial when you go for higher Mach number. So we started this problem with Mach 2. So if you work out the same problem with Mach as maybe 4 or Mach 4, then you will be able to see the benefits of inlet pressure recovery with decelerating the flow over multiple shock trains. Okay. In the afternoon, we will continue with the application of these shocks in supersonic inlets. Okay. Yeah, so it's like a normal shock.
And when the Mach number increases, this is attached, and when you a higher Mach number,
We will be discussing that. What you're talking about is when you have a shock further away from the inlet, which is called a subcritical mode of operation. When this shock is attached to this one, it's a critical mode, and if the shock goes into this one, it is supercritical mode. We will discuss this in the afternoon one. But then if you have a spike or something like that, I'm talking about inlet which is a sharp inlet. It's not like a blunt with like a commercial ones. If it's like a like the edge is sharp, so we can hold the shock there. If it's blunt, then it will be like a shock will be thrown out. Seen in the this is happening outside the inlet. The whole idea is that once we have a shock wave that is being formed. So here is the engine here. We're talking about it. Let me put it like this. It's a okay. This is a sharp one. So once you have a shock wave, there are a lot of other things we're going to discuss today. We don't want to lose the flow off. This is what we call as a spillage. We're going to lose it. So the other benefit is that here it is greater than 1, less than 1, then this object knows that this is coming here. Okay, but then if this shock is drawn into it, which is here, then there is no mass loss spillage. There are two things we need to look at. One is the pressure recovery, phi d, and the mass loss spillage. So these things we'll be discussing this afternoon. Good question to start from this afternoon.